Okay, we're going to have a look at a third example. In this question, we're going to have a look at proving by contradiction the fact that there are infinitely many prime numbers. This question also involves, like the last one, also involves a little bit of a trick, and you have got to learn it, and you need to be able to remember and use this in the exam. So first things first, I need to state an assumption, and it's going to be opposite to the thing that I'm trying to prove. So rather than proving there are infinitely many prime numbers, I'm going to make an assumption that there is a largest prime number. I'm going to call my prime numbers, I'm going to call them Pi. So P, my prime number, I, so P1's my first prime number, P2, P3, and all the way up to my largest prime number, which I'm going to call Pn. So I've got n prime numbers, Pn is my largest. So that's my assumption, and that's what I'm trying to contradict. What I'm going to do, and this is the trick, I'm going to put x equal to the product of all of those primes. So P1 times P2 times P3 times all the way up to my largest prime, Pn. And then I'm going to consider what happens if I take y and I take my x value and I add 1 to it. So I've taken x and I'm adding 1. So I've got y equal to x plus 1, and what I'm going to do then is I'm going to consider what happens if I take my y and I divide it by each of my prime numbers. So P1, first prime number, that's going to be 2. P1 divided by 2. Well, if 2 divides into x, because we know it does, because it's going to be a factor of x, if I try to divide it into x plus 1, it's going to go in, I'm going to be left with a remainder of 1. So it's going to equal something with a remainder of 1. Similarly, if I take the next prime number, 3, so that's P2, second prime, and I divide it y by that second prime, well, second prime, 3, divides exactly into my x, because it's one of my factors of x. So if I've added 1 onto x to get my y, it's going to divide in, and it's also going to leave me with a remainder of 1. So it's going to equal something, remainder 1. In fact, that happens for all of my prime numbers because they're all factors of x. So if my prime numbers divide exactly into x, when I divide them into y, I'm going to be left with a remainder of 1. So y divided by Pi has a remainder of 1. So none of my p's are a factor of y. Now that means either one of two things. So either y is a prime number, in which case we have a look at how big it is. Well, we've taken all of these primes, they're all bigger than 1, and I've multiplied it by Pn, which is supposed to be my biggest one. So y is going to be a lot, oh, and then I've added 1 onto it as well. So it's going to be a lot bigger than Pn. So y is a prime number, then this contradicts my assumption, I can't say that word at all today, assumption that Pn is the biggest, because we've just made y a lot bigger than Pn. So either that or y is not prime. So if it's not prime, it must have a prime factor. Well, we know that all of our prime numbers that we're aware of so far, P1 through to Pn, are not factors. They've got a remainder of 1. So none of P1 to Pn is a prime factor of y. Therefore, there must be another prime factor that's bigger than Pn. So that also contradicts my assumption. So this contradicts, this is my either, onto my or, this contradicts my assumption, really can't say that word today, that Pn is the biggest. So either y is prime, in which case y is the biggest prime, or y is not prime, and there must be a bigger one, bigger than Pn, that divides into it, otherwise it would be prime. So that Pn is the biggest. So either way, we've stated a contradiction. Therefore, we can say our conclusion. Therefore, there are infinitely many prime numbers. And job done. So for this question, it's all about remembering we need to use this x as the product of all of our primes up to this value that we're assuming is the biggest. Looking at y equal to that product of primes, add 1, and we can work out, we know we've got a remainder of 1, and we need to look at those two cases. So either y is prime, or if y isn't prime, then it must have a prime number that's not one of the original ones, 1 to n, and that must be bigger than P1 to Pn. Remember, Pn's my biggest one, so I've got that contradiction. Therefore, I've proven by contradiction that there are infinitely many prime numbers. At the end of the second question, we had a look at proving that root 3 was irrational. I made a bit of a leaping statement. I made the statement that if 3 is a factor of x squared, then 3 is a factor of x. It's actually quite an interesting question, and it's another question that we can prove by using our proof by contradiction. So as a little extension, I'm going to give that a go. So if 3 is a factor of x squared, then 3 is a factor of x. So I want an assumption, and that's going to be that there is an x such that 3 is a factor of x squared, but not a factor of x. But not a factor of x. So 3 divides into x squared, but it doesn't divide into x. Well, so if 3 is not a multiple of x, then it's got two options. So x is either going to equal to 3k plus 1, so a multiple of 3 adding on 1, or we've either got that one, or we've got x is equal to 3k plus 2. So 3k plus 3, then that was also a multiple of 3, and that's going to break my assumption. So what I'm going to do is, I've got my assumption that 3 is a factor of x squared, but it's not a factor of x, and I'm going to try and contradict that. So I'm going to consider those two possible options. So the first one, x is equal to 3k plus 1. So x squared would be equal to 3k plus 1 all squared. Well, that's going to equal 9k squared plus 6k plus 1. If I factorise that as much as I can bring a 3 outside, and I can do 3k squared plus 2k plus 1. So I've got a multiple of 3 plus 1. So x squared, not a multiple of 3. So 3 is not a factor of x squared. So that's my contradiction. So it doesn't work with 3k plus 1. Let's have a look at 3k plus 2. So x squared is going to equal 3k plus 2 all squared. So that's going to be equal to 9k squared plus 12k plus 4. I'm going to factorise this. I'm going to be quite clever, because what I'm trying to do is I'm trying to prove that it's not a multiple of 3. So I'm just going to leave 3 outside my bracket. I'd end up with 3k squared. I'd get plus 4k. And what I want to do with this plus 4 is I want to split it into 1 plus 3. The 3 I can bring as put it inside my bracket, because I've got my common factor 3 outside. So that would be plus 1 lot of 3, and then I'll be left with my 1 left over. So I'd get 9k squared plus 12k plus 3 plus my extra 1 to bring me up to my plus 4. Well, this is also not a multiple of 3. Which gives me a contradiction. So my assumption was that there's an x, that 3 is a factor of x squared but not a factor of x. So I've looked at all the possible numbers where 3 is not a factor of x and proven that 3 then is not a factor of x squared. I'd always end up with a remainder of 1. So I've got my contradiction. So under both of the two, so this contradicts the assumption that 3 is a factor of x squared, and therefore, state my conclusion, if 3 is a factor of x squared, then 3 is a factor of x as well. Shift that up a little bit so we can see it, and we've done it. So we use that fact within our proof of proving that root 3 was irrational. If you want to prove it, you can actually use proof by contradiction. We had to consider 2 options. We had to consider x being equal to 3k plus 1 if 3 wasn't a factor of it, and the other option of 3k plus 2. That covers all the possible multiples, all the possible numbers, integers that have not got 3 as a factor. Under both of those cases, we achieved our contradiction that we proved that x squared was not a multiple of 3, so that contradicted the assumption that 3 was a factor of x squared, got the contradiction, and we've proven that point. Okay, excellent. Have a look at some of those other questions and drop me a line if you need any more help.